We discuss IPv6 in today's lesson. IPv4 has played a central role in the internet working for many years. However, 32 bits of the IPv4 address eventually cannot accommodate its explosive growth. New version IPv6 was designed to interoperate with IPv4 since it would take years to complete the transition from v4 to v6. Two major changes from IPv4 to IPv6 are longer address field and a simplified header format. IPv6 uses 128 bits for addressing that can support up to 3.4 times 10 power 36 hosts. IPv6 also simplifies header format so as to speed up processing of each packet header. All fields are of fixed size in IPv6. Let's take an overview of IPv4 and IPv6 comparison. Both keep the version. IPv6 drops header length, ID, flags, offset, and header checksum. IPv6 further replaces the datagram length by payload length, protocol type by next header, time to live by hop limit, and type of service by traffic class. It also created a new field, flow field. The IPv6 header consists of a required header and optional extension header. The format of the basic header is shown in the figure. The traffic class is intended to support differentiated services. The flow label field can be used to identify quality of service requested by the packet. In IPv6, a flow is defined as a sequence of packets from a particular source to a particular destination for which a source requires special handling by the intervening routers. Payload length indicates the length of data excluding header, with 16 bits allocated to this field. The payload length is limited to 64 KB. But it is possible to send larger payloads by using the option in the extension header. To support extra functionalities that are not provided by the basic header, IPv6 allows an arbitrary number of extension headers to be placed between the basic header and the payload. The extension headers are trained by the next header field. Extension headers act like options in IPv4, but are more efficient and flexible. IPv6 allows a payload size of more than 60K bytes called a jumbo packet by using an extension header. The use of larger payload size is promoted by high-speed networks, by big data applications, and by supercomputing applications. The figure shows the format of the extension header for a packet with a jumbo payload. The next header field identifies the type of header immediately following this header. The value 194 defines the jumbo payload option. The payload length in the basic header must be set to 0. The option length field specifies the size of the jumbo payload length field in the bytes. Finally, the 32-bit jumbo payload length field specifies the payload size, which can be as large as 4 GB. IPv6 allows only the source host to perform fragmentation. Intermediate routers no longer perform fragmentation. The rationale is to speed up routing at the intermediate routers. If the packet length is greater than the maximum transfer unit (MTU) of the network, a router simply discards the packet and sends an ICMP error message back to the source. A source host can find the minimum MTU along the path from the source to the destination by performing a path MTU discovery procedure. One disadvantage is that the path between a source and destination must remain reasonably static, so that the path MTU discovery doesn't get outdated information. If a source wants to fragment a packet, the source will include a fragment extension header, as shown in the figure, for each fragment of the packet. Like IPv4, IPv6 allows the source host to specify the sequence of routers to be visited by a packet to reach the destination. This option is defined by a route extension header, shown in this figure. IPv6 addresses are divided into three categories: unicast addresses, multicast address, and anycast addresses. The dotted decimal notation would be rather long when applied to IPv6 long addresses. A more compact notation to use is hexadecimal notation. Because IPv4 networks and hosts are widely deployed, migration issues need to be resolved to ensure that the transition from IPv4 to IPv6 is smooth. Current solutions are mainly based on the dual IP layer or dual stack approach, whereby both IPv4 and IPv6 functions are present. Routers support both IPv4 and IPv6 protocols and can forward both types of packets. When islands of IPv6 networks are separated by IPv4 networks, one approach is to build a tunnel across an IPv4 network connecting two IPv6 networks, as shown in this figure. A tunnel is a path created between two nodes so that the tunnel appears as a single link to the user. A tunnel is typically realized by encapsulating each user packet in another packet that can be forwarded along the tunnel.